Hi everyone, so today we are going to be looking at half-life due to radioactive decay. Now for this problem set there is actually two PDFs. So the first one is the lab and then the second one is the actual problem set. So what we would like for you to do is to do part of the lab and then do the problem set. But in class we're going to be focused on finishing up the poster, right? So we need to make the poster because we need it for Wednesday. So anyways, we'll start with this guy. And you want to send it to Notability. I wanted to send it to Physics. Say down here, and then do the other one as well. Okay. Import. Open note. So I think what I want to do is, where did it go? Did it go all the way to the bottom? No. Oh, it's right here. Okay, so first we're gonna start with this. We're just gonna skip this one. Okay, so we're gonna skip the experimental part. We're just gonna skip it. Instead, what we're gonna do is we're gonna do the computer modeling activities. Now, it's pretty interesting, and it'll help you understand the concept of half-life. So, let's go. Let me find this. Okay, so you want to go to link. Play. Run this one. Okay. It'll take a few seconds to load. Okay, so now we got the problem set. Okay, so it says, or you can search Google, right? You could actually search it. I'm gonna go with blue. Okay, what happens to an atom after its decay? Is it gone? Okay, so we're gonna look at the half-life tab first. So wrong one here. So so these are the different tabs that the problem set is talking about. So we're gonna look at what is this concept of half-life. So here we have a graph that tells us something that is happening. So here we have carbon 14 that is it's like frozen. Right, so you can put a whole bunch of carbon in here and see what the half-life is. Right, so the half-life is a little bit over 5,000 years. Now it's pretty interesting. Some of these some of these take longer to actually decay into nitrogen. Okay. Some of them last longer. Alright. Okay, what happens after an atom after it is decay, right? Is it gone? No, it's not gone. It turns into a different isotope. You can call it isotope or atom. That's either one is fine. Right, so the number of nucleons definitely change. Next, can you predict when an individual nucleus will decay in a group of many nuclei? Can you predict when the next nucleus is going to decay? Right, so this is a pretty interesting idea of half-life. So if you put a whole bunch of them in here, right? It's kind of glitchy. I don't know why. But if you put a whole bunch of them in there, you can start to see that they're not really predictable. Even though the half-life is right here, they don't all decay at that point, right? Some of them are earlier, some of them are later. So it kind of tells us something about decay. Can you predict the individual? So no, you cannot. No, you cannot. If there's a group, can you actually predict when they're going to decay. So that's a good question in itself. And let me just double check my notes here. Da-da-da. I'm pretty sure you cannot as well, right? So you, in a group, so you can only have a general idea of when it should decay, but you cannot predict exactly when it's going to. Okay, let's go to C. So now this is the decay rates lab. So we go, right, so we look at decay rates, okay, and the question is describe the graph. All right, okay, what are the two things graph and how are those two things related to each other? Right, so let's go to the graph, and you can scroll a little bit here. Once you scroll, then you let it go. Okay. Right, so if you didn't see that, so the graph describes the percent of elements remaining over time. Right. So that's what it describes. Percent of elements remaining over time. Okay. So so if we're looking at that y-axis, that's percent remaining, and then here's our time. Now that's pretty interesting. There's a point when they cross here. And if half-life wasn't marked on the graph, how can you describe where to find it? Where the two percentage crosses. All right. Does that make sense? I think so. Yep. See where they cross right here? That'd be the half-life. Cool. Okay, optional. Oh, no, not yet. So it wants you to compare uranium and carbon. So uranium and carbon. So if you look at the scale of carbon, you can see it's in like thousands of years. But if you look at uranium, it's like billions of years. So the half-life of uranium is much, much longer. It's a very long time. Thousands of years. Okay. So if we're figuring out like how old things are in thousands of years, this is for billions of years. Billions of years. Okay. But they're for figuring out how old things are. Okay, getting out of the game, see the term. Okay, so this is pretty interesting, and you can explore this by yourself, but I'll show you guys. So there's a dating game, right? So you're gonna figure out like how old things are. So for example, let's look at this here. Right, so it wants us to estimate the age of the wooden cup, and there's a little green arrow here that you can move around. So if there's only, right, so it tells us that it'd be, if it was carbon 14, there will be about 88.2% left. So I'm gonna find about 88.2 or something like that here. So we're looking at 88.2. It's about 1,000 years, maybe, right? So time is 1,000 years, and we can check that. So that's nice, and it has a little sound. Check this guy. Right, so we can look at the human skull here. So we can see that it's definitely going to be more than 18,000 years. So maybe it's going to be like 25,000 years. I don't actually know. Maybe 40. Right, so it's about 40,000 years. Okay. So there's this game that you can kind of play around with and kind of figure out how old things are. But here's 14. And this is sort of how carbon dating works, is we look at how much carbon 14 is there and figure out how old it is from there, from all the other points of data that we have. So it is probably at least so it's probably about 15,000 years old. Yep. So okay, have fun with that. Now I'm gonna work on some of the problems here, and these problems they're actually not too bad. They're just kind of you just gotta think about them, and they're kind of interesting. I don't know how much time I actually spent on this video, but hopefully it's not too long. Okay, so here we have iodide 31 is used to destroy thyroid tissue. Okay, the half-life of iodide 31. So I-31, 131 is 8 days. Okay. If a hospital receives a shipment of 200 grams, how much will be left after 32 days? So 32 days, 32 divided by 8 is 4. So at least 4 half-life cycles will pass. Okay, will pass. So we start at it's kind of like this. So you start at 200, right? Then it's gonna be 100, right? So that's one half-life cycle, right? Then it's gonna be 50. It's gonna be 25, and then it's gonna be 12.5. It's gonna be 12.5 grams. How do I know that? Well, this is one life cycle. This is 2. This is 3, and then this is 4. So after 4 half-life cycles, there will be 12.5 grams left. Okay, but this is the way that you kind of have to like think about it. Now there probably is an equation for calculating half-life. Well, I know there is, but we don't really have to use it. Okay, so let's go next one. The half-life of carbon-14 is 5,000, so C14. I'll do it like this, 5,730 years. A piece of linen found today contains carbon-14 and gives an activity of 15 counts per gram. Alright, so today, 15 counts per gram of carbon. If an anthropologist found an ancient piece of linen believed to be to date back to the Neolithic period that only gives 7.5 counts per minute per gram of carbon, how old is this ancient? So ancient be 7.5 counts. Okay, well if it's half the count, right? If you remember the Geiger counter thing that counts like radioactive decay, that's what this is talking about. So right, so if this is like normal amount, right, this is your full amount, this would be your half amount. So it looks like, right, the ancient cloth linen will be at least 5,030 years. Okay. That's because the count has dropped, right, to 1/2. So yep, has to be that. Okay, next one. Okay, so you can kind of see that the problems are kind of like this, and we can definitely figure this out. Next one. Okay, mercury 197. Mercury is Hg, if I remember correctly. 197 is used for kidney scans and has a half-life of 3 days. If the amount of mercury needed for a study is 1 gram, and the time allowed for the shipment is 15 days, how much mercury will be needed? Okay, that's pretty interesting. Okay, so in this problem, you kind of go backwards, right? So you start with 1 gram. So after 1 cycle, it would be 2 gram. Let's just write G. All right, so that's 1, 2, and now 4. Okay, so it's gonna be 3 days, 15 days, divided by 3 days. So you need at least 5 half-life cycles. 5 cycles, so that's 1, so that's 1, 2, 3, so I need more, so 8 grams. It's gonna be 16, and then it's gonna be 32. Right, so that's 1 cycle, 2 cycle, 3 cycle, 4, and 5 cycles. So you need at least 32 grams. 32 grams of HG197 for you to have at least 1 gram left. So probably ship like, I don't know, 50 or 100 grams. Right, that'd be good. Okay. Next one, and then I think I'm gonna let you guys try to figure out the rest of these, because I think this video has gone on pretty long. If the half-life of uranium-232 is 70 years old, how many half-lives will take for 10 grams to be reduced to 1.7 grams? This one is pretty similar to the one before, so I'll let you do it. But I think I'm gonna do the graph one here, and then stop. Okay, so it says use the graph to answer questions 5 to 7. Based on the graph, what is the half-life of cesium-137? Okay, so we have cesium, and we're looking for the half-life. Now, the half-life is when the full amount goes to 1/2, right? So it starts at 100, maybe I'll say grams. So we're looking for 50. When does it hit 50? Right, so here's 50, and you can kind of see that it's 50 after about 30 years, right? So here's our x-axis, it's in years, our y-axis is amount. Okay, so now we want to know, is it always 30, right? Is it always 30? So we're going to go from 50 to 25. 25 is like right here. Alright, so you can see, okay. And the 30 years has passed, right? And then 25, so we're going from 100 to 50 to 25 to 12.5. So 12.5 is kind of like here. That's it looks like, based on the graph, what is the half-life of cesium? About 30 years. 30 years. Okay. Approximately 30 years, I suppose we can say that. What is the most precise method for predicting half-life from a graph like this? So the most precise way to actually do it is to calculate it. And we can calculate it like this. Okay, so we know, right? So we know that, okay, so we have to count the cycles, I guess. So here's 1 cycle, here's 2, here's 3, here's 4, here's 5, 6, 7, and then 8 cycles. So we know that there's 8 cycles, and want to know the total number of years. So the total number of years is, in total, is 240 years, right? So 240 years for 8 cycles to occur, right, to be about 0. So then it's going to be 24 divided by 8, it's going to be 30, right? 30 years. Okay. So you can calculate total years, right? Total years divided by cycles, right? Half-life cycles. Okay, if you start with 500 gram, okay, of cesium, how many years would it take for it to be below 10 grams? I will tell you what the answer is, but I think you can figure it out yourself. At least 180 years. Right, but you start with 500, and then you want to look for how many cycles there'll be, and you're gonna figure it out. Okay, all right. Bye. Have fun. Good luck.